we're going to look at today, we're going to look at square roots and then wrap up and kind of complete our view of numbers. Okay? A square root of number is, here's the definition, mathy definition. It's the solution to the equation x squared equals b. A perfect square is any number with a whole number square root. Any number whose square root is a whole number. Okay. And we're going to make a list of the first 10 of them, because they're pretty important numbers for you to know. In particular, we can generate the list in the following way. Let's start at 1. So what's 1 times itself? What's 1 times 1? Okay, there's our first perfect square. What's 2 times itself? What's 3 times itself? 16, 25, 36, 49, 64, 81, and 100 are the first 10 perfect squares. We get each of those numbers by taking 1 times itself, 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6, 7 times 7, and so on. And you can make more of these. You could do 11 times 11, which is 121. Do 12 times 12, which is 144. Do 13 times 13, which is 169. 14 times 14, 196. And you can keep going and keep going and find all the perfect squares. Okay? So for example, I could give you a handful of them. Like say root 49. What's the square root of 49?
7.
Hey, we're on a roll. How about minus the square root of 4? Minus the square root of 4 is negative 2. Minus the square root of 121? Plus or minus the square root of 16? Plus or minus 4. Keep in mind this symbol, plus or minus, stands for 4 or negative 4, is what the plus or minus symbol stands for. Okay? This stuff's pretty quick. If you know the perfect squares, then working backwards is pretty easy. Well, what happens if we need to estimate they're not perfect squares? And let's say your calculator batteries have just died and you have no resources whatsoever. It's just you, your brain, and some paper and pencil. How the heck are we going to estimate square roots? We don't.
You look at, so you do like a number, and then you look at a number that's below it and a number that's higher than it, and you like find the number in the middle.
Yeah, absolutely. Did everyone pick that up? No? Let's repeat that a little bit slower, because this is exactly the method we want. Sandwich the square root we're looking for that we don't know between two numbers that we do know. We do know the root of 25. We do know the square root of 36. And 34 is somewhere between them. So if you find the square root of everything, 5, 6, and you know that the square root of 34 should be somewhere in between them. Now the question becomes, what whole number is square root of 34 closest to? Is it closest to 5, or is it closest to 6? How do you know? 34 is closest to 36. So the square root of 34 should be closest to the square root of 36, which is 6. You can think of it visually as like, you can draw yourself like a number line. And if you put, say, 25, 25 is at one end, 36 is at the other, where is 34 closer to? What end? 34 is a lot closer here. So if you take the square root of all of these, that means that square root of 34 should still be closer to this end, which is closer to 6. So estimating the square root of 34 means it's pretty close to the nearest whole number would be 6. So square root of 34 to the nearest whole number would be 6. Okay? To the nearest whole number, the nearest integer. Okay? And there's some more examples on the backside. To the nearest whole number. If we estimate that square root to the nearest whole number, then we can estimate it using this squeeze method, this in-between method. To find the square root of these other numbers, please. Looked at square roots, we can complete our view of classifying numbers. Okay. If you recall, back on last Monday, or was it last Monday? Yeah, last Monday, we looked at a way to name and classify types of numbers, and we had this beginning kind of picture. If you remember the Venn diagram we drew. Does anyone remember what's the middle? What's the most central? Natural numbers. The innermost workings were the natural numbers. And natural numbers were counting numbers. They were numbers that you could count on your hands, fingers, and toes. They are positive whole numbers. Are natural numbers. Okay. And we then said that if we take the positive whole numbers and we add in all the other whole numbers, we get this bigger set called the integers. And we said that integers can be any whole number, positive or negative. An integer can be any whole number. And we had some examples in here. We said that natural numbers would be like 1, 5, 10, whatever. Integers could be like 2, -4, -5, positive 100. Any whole number, whether positive or negative, is an integer. Then we said, well, that's not good enough to describe all the numbers because we could have fractions. We could have numbers that are described as the ratio of integers. So we call those rational numbers. And we said rational numbers are any number that could be expressed as a fraction of whole numbers. So those include like any whole number specifically. You can turn any whole number into a fraction by just dividing it by 1. So like 7 is a rational number. Any fraction is clearly a fraction, clearly a rational number. Say like 4/5 is a rational number. We said that any decimal that terminates or that ends can be written as a fraction, like 0.5. What's 0.5 as a fraction? 1/2. Okay, that's clearly a fraction. Any decimal that terminates. And we also said any decimal that repeats, like 0.6 repeating. What's 0.6 repeating as a fraction? Not 0.6. Anyone know what 0.6 repeating is as a fraction? It's a common one. Nope. Nope. Oh my goodness. Close. 2/3 is 0.6 repeating. 1/3 is 0.3 repeating. 2/3 is 0.6 repeating. this isn't enough to complete our view of numbers because there are other numbers. There are numbers that if you write them as decimals, they never repeat and they never end. Can anyone think of a number that if you type it in a calculator and you get it right as a decimal, it never repeats and never ends? What's one?
0.78.
You can construct one on your own, sure. You can just keep writing random numbers at random. There's definitely one I expect you all to know right now. Pi is one of them. Pi doesn't fit anywhere in here. Yep, pi does not fit anywhere in there. Other numbers that never repeat and never end, these are important ones. Like square root of 2, like the square root of 3, like the square root of, say, 8. The square root of any number that's not a perfect square never repeats and never ends as a decimal. There's one other really famous one you might not know. You probably haven't experienced much of it yet. But there's my personal favorite number. Is this one. This is my favorite number. It's called Euler's number. It's represented by the letter E. It's pretty important. It's pretty important. It's actually more important in math than any of those other numbers combined. It's more important than pi.
Oh my god.
For sure. Yeah. But it's specific to it's. We'll talk about it later in the course as to what we use the letter E for. But it's really actually pretty important. It's approximated about 2.78, blah blah blah, so on. It's between 2 and 3. It's pretty important. These numbers that never repeat and never end as decimals are called irrational numbers. They're called irrational numbers. Okay? And when we combine this grouping of irrational numbers with this grouping that we've already constructed, then all of these things, anything that fits into anywhere in this diagram, is called a real number. Okay. It's called a real number. So we're going to take our diagram here, and we're going to take a couple lists of numbers and see where they fall. Okay. So for example, square root of 64. What's the most specific category that square root of 64 falls into?
Real.
Natural numbers. Why natural? Can you simplify root 64? Yeah, it's 8. So because positive 8, what's the best category it falls into? That's the natural numbers. Okay. Well, now we'll work backwards. Because if you're a positive whole number, then you're definitely any whole number, which is an integer. And if you're any whole number, you're definitely can be written as a fraction. And if you can be written as a fraction, then you're on that list, so you're definitely a real number.
Oh, that's true.
Okay. How about negative 5? What's the most specific label you give negative 5?
Integer.
Integer. It's not positive whole number, so the best we can do is any whole number, which is negative 5. And if you fit here, again, if you're a whole number, then you're a fraction. And if you're a fraction, then you're real. And we'll play that game so on. Negative 9 is a natural number. Or sorry, root 9 is a natural number. That's 3. Definitely a whole number then. It's definitely a fraction. And definitely a real number.
Oh, you're going.
Yeah.
And the whole number 2.
Wait.
Please
all.
Integer, rational, real.
Jack.
Jack has had a wait.
2 is a positive whole number, so it's definitely a natural number.
What about the other
And from looking at your diagram, if you're natural, then you fit into both the integers and the rationals. And since it's on the diagram at all, it's a real number.
Okay, what's the irrational?
Put them in order from least to greatest. Okay. Your last task for today is to take the second column here and fit the numbers into the appropriate boxes.